All right, thanks for the introduction. You guys hear me all right? Okay, they're not having quite as much of a party next door. I'm Ethan, I'm at Iowa State University. I'll talk a lot about aerosol jet printing, so I kind of break this up into three parts. I'll give a very brief introduction to aerosol jet printing for those who aren't familiar with it. And then the kind of first half of the technical talk is about this process monitoring and control. So how do we get this aerosol jet printing process to be more reliable? And then the second half is some kind of newer work we're doing on motion lighting for conformal printing. I'll try to tie those together. So the disclaimer here, the first half of this is describing a lot of it as results of the next funded projects we were working with Optimec to integrate our process monitoring and control tools for aerosol jet printing onto their equipment. All right, so for aerosol jet printing, very briefly, we take a liquid ink, we're atomizing it into micron-sized droplets. We can move those droplets into a print head. They're just suspended in a gas flow, and then we can focus them down and print them through a nozzle. So the nozzle may be 100 micron diameter, and what we're printing is 1 to 50 micron wide line. It's a very nice technique for rapid prototyping and all digital control, but it is a slow process compared to all the roll-to-roll methods here. And there's three kind of key limitations that I'll mention here. The one that I'll focus the most on is this process drift issue. I'll describe that momentarily. And then low throughput and some overspray issues, which I'll also describe a bit. But one of the big kind of benefits of this, something that we're very interested in leveraging, is when we're printing, we have our print nozzle up to about 5 millimeters off the surface that we're printing on. So if we're trying to print onto a curved surface, we have a lot of tolerance for printing onto that you wouldn't have with something that needs to maintain a very strict distance from the surface. So aerosol jet printing has been kind of explored for a number of applications. I won't dive into that, but electronics packaging, it's like RF devices, and conformal printing on 3D surfaces. All right, so what's the kind of problem we're trying to solve here? So for the aerosol jet printing process, is the generic manufacturing process. Three things that I care about are going to be the deposition rate, how much material am I putting on surface, the line width, is that resolution changing over time, it's kind of vague, line quality. But the kind of important thing here is that the deposition rate is an input. If your deposition rate is changing, everything else in your process is likely going to change. We ran some tests to just show a kind of representative process drift in aerosol jet printing. And the test here over the first couple hours of printing, the black data points are the thickness of samples, so that's your deposition rate. And it's noisy for those first couple hours, and after that, you get this really steady decay. And we want to be able to pick that up in real time as we're printing and not go back after 6 hours of printing and figure out that something has changed in the process. So the technology that we developed for this, and this is over the last 6 or so years, is to implement the sensor in line in the process. So this is our kind of full aerosol jet printing process. We're putting the sensor just upstream of the print head, and all we're doing is shining light in from one side and measuring how much light gets scattered off those aerosol droplets. These micron-sized droplets, even if they're completely transparent, they scatter light extremely effectively. Think about fog as you're driving at night, your headlights are bouncing off of everything. That's what these aerosol droplets are going to do. So we can get a very quick quantitative measurement that tells us how much aerosol is in here, and we can do that in real time while we're printing. So there's three big areas where we want to apply this. The one that I'll talk the most about is closed loop control. So if we can detect a change in the process in real time as we're printing, we can adjust process parameters, adjust our printing parameters to compensate for that, and a much more reliable process. And just kind of for completeness here, the other two, so we have a continuous data stream as we're printing, and we can coordinate this with where are we in the physical part. And so we can go back after we've printed something and say, okay, did I print what I actually thought I wanted to print? And we can see if there's more or less material deposited in certain areas, where should I be looking for defects in this part? If we had a little bit less material on one of the contact pads in this serpentine, that maybe doesn't matter for the functionality. If it happens in the serpentine itself, that's a big red flag. And then the last kind of broad bucket for this